but a well-designed audio amplifier will be able to ignore frequency response, so that's okay. But this is a very, very nice source. So one of the things we're going to assume to begin with is we want to use a single power supply. So we're going to use a 12-volt power supply. Going to all of these, 12 volts, 12 volts, 12 volts. That allows us to use a single power supply for everything as opposed to having to worry about multiple different power supplies in our design. So we picked a 12-volt power supply. Again, buffer stage is going to allow us to isolate the signal coming from here, from that input resistance. The output stage is going to allow us to match the current we need to get this 0.1 watts of power going to V out. And then finally, the gain stage is going to allow us to actually get the amplification gain we need to get our design. So with that in mind, let's start designing these. So we're going to start with that buffer stage. Or input buffer stage, as the book calls it. So, we've talked about a couple of different amplifier designs. What amplifier design could we use to isolate an input from an output? That's right, the emitter follower. And so we're going to use an emitter follower design. And the book actually is going to give us some specifications that we can pick kind of on our own, but these are good initial base specifications. So we're going to assume our BJT has a beta equal to 100 just to make our life easier. We're going to assume that our ICQ, our quiescent current, is 1 milliamp to the DC value. And we're going to assume that we have a VCEQ of 6 volts. And these are very good design applications because beta is a very common value. 100 is a very common value for beta. ICQ being 1 milliamp is likely to be stable, and VCEQ being exactly half of VCC is a very, very good value to try and drop to. With that in mind, another thing we can pick, just to kind of make our life again easier, we can say that R1 equals R2 equals 100 kilo ohms. This is a bit more arbitrary, but it makes sense with the math we're doing and some of the different applications you have to solve. So let's go ahead and draw our amplifier, what it would look like to begin with. Again, we have our VS, which is our microphone. We have our RS, it's just that 10 kilo ohm resistor. And we're going to go through some capacitor, we're not going through the design application for. That's one of the things we're ignoring is the capacitors regarding frequency response. We can go back and add those next chapter. We know that VCC is 12 volts. And again, we said R1 is equal to R2 equals 100 kilo ohms. This is a emitter follower or a common collector, which means we get to not have a collector resistor. Makes our life nice and easy. And then the only thing we have to really design in this case is going to be RE. Which we kind of know because we can solve for IB very easily. We know IC. IB is just going to be 10 microamps. So we could get a specific value for RE, or we can just say RE is approximately going to equal VCC minus VCEQ over ICQ, which equals 12 minus 6 over 1, give me 6 kilo ohms. We're approximating this because we're trying to get a practical value. If you actually get the correct value, it's 1 over 1.01. Because remember, IEQ is actually IBQ plus ICQ, but because it's the scale, that would be a 5.94 kilo ohm resistor. It's one of the things the book just skips over. It just says, hey, it's 6 kilo ohms. 5.94 kilo ohm resistor would work. 6 kilo ohms is going to give us a good enough approximation of what we want, that we can go from there. And we can also get our small signal parameters. We can get R pi, Yes.
Yes.
Someone had a question. It cut off though. Oh, is it me echoing?
Yeah, I accidentally unmuted the classroom. That was my bad.
Okay, thank you. I just didn't want to talk over someone. I know I go fast sometimes. Again, we pick 6 kilo ohms because it's a good approximation. 5.94 would be the actual value we're trying to hit. But again, you don't really, 6 kilo ohms is good enough for the design. In this case, from there, we can see that R pi is going to equal beta VT over ICQ. You can get that pretty easily, and that's 100 times 0.026 over 1 milliamp, which is going to equal 2.6 kilo ohms. We could solve for transconductance. We're not going to use it in the problem solving in this case because we don't really care. We're going to end up using beta is equal to 100. The book doesn't bother solving for it. If you want to, remember GM is equal to ICQ over VT. Which is going to equal 38.46. Just good practice to do. You don't need it. We're going to assume RO is infinite. Next thing, we're going to solve the circuit, but we're going to assume one very big thing. We are ignoring loading effects from next amplifier stage. So basically we're saying that, yes, we're going to be feeding the output of this V out right here, which I should have put in there to begin with, into the next amplifier stage. We're going to assume its load resistance is large enough that it doesn't impact our circuit. We're ignoring its loss. That will give us some issues, and we should look at how these circuits interact overall on a larger scale during the design process. But again, this is a kind of a brute force rough approximation that works through different practice problems. So it's a good theoretical understanding of things. We are simplifying things still. Keep that in mind. From that, we can redraw the circuit in its equivalent form. Again, short that to ground, short that, and then we can say Vs, 10 kilo ohms, 50 kilo ohms, and there's a path from base to emitter. That's 2.6 kilo ohms. And then there's collector, it's the ground. Path from collector to emitter is beta IB. And this is just 6 kilo ohms. V out. This is our equivalent circuit. You're practicing doing that a lot this week. Make sure you can do that on your own. In this case, V out equals beta plus 1 IB times 6 kilo ohms. IB is going to equal, IB is going to be a little more complicated than that, but it's going to equal, well, let's do it the correct way. So we'll call this voltage right here, VB. VB equals IB times 2.6 kilo ohms plus beta plus 1 IB times 6 kilo ohms, which is just V out. So RIB is going to equal 101 times 6 is 606 plus 2.6. Again, I'm not doing this one symbolically, I'm doing it with math, so then it equals 608.6 kiloohms. And then we can also say that Ri equals R1 in parallel with R2 in parallel with RIB. So it's going to equal 46.2 kiloohms. Huh. That's not right unless I did something wrong. So, yeah, okay. Oh, I'm sorry. They said that R1 equals R2 equals 200 kiloohms. Like, why is that wrong? So they basically said R1 in parallel with R2 equals 100 kiloohms. I apologize for that. So this is 100 kiloohms right here, not 200. And they actually didn't worry about. Okay, well, that's fine. They actually just said R1 parallel to R2 is 100 kiloohms. They didn't give values for R1 and R2. So in reality, I have to change this. I apologize. So it's not 50. So it's R1 in parallel with R2 in parallel with RIB equals 100 kiloohms in parallel 608.6 kiloohms. That will equal 85.9 kiloohms for our input resistance right here. Sorry that I did that incorrectly. Read their numbers wrong, so I'm really confused there. Okay, so from there, we can go back and say that VB equals RI times VS over RI plus RS, which is going to equal 85.9 over 95.9 times VS. And then at which point we can say that IB equals VB over RIB. And I'm going to go ahead and erase my circuit over here and write the answer. And the book does not go through any of these derivations or even draw the next circuit. They just give you the answer. So I apologize. I made a mistake there. And so now they can say, okay, we look back at this, we can say that VB over RIB equals IB, which means we can say that VS times 85.9 over 95.9 times R pi times 1 over R pi plus beta plus 1 times 6 kiloohms. Then we can put that back into V out, and we'll get that V out equals 606 kiloohms times VS over 608.6 kiloohms times 85.9 over 95.9. And we'll get the V out in terms of VS or AV, our voltage gain, is going to equal 0.892 volts per volt. And this is what we wanted to know, because that means that our 10 millivolt peak-to-peak signal is now 8.92 millivolt signal coming out of here. That's one of the things we're going to need to know to design the gain stage. So we need to know the scale of V out. That is our input buffer. We have taken our signal and we have dealt with the loading effect of this large 10 kilo ohm resistor. And now we're going to take it to the next stage. And if we go back to right here, the next stage would be gain, but we need to know our total gain. So we know the input to the gain is 8.92 millivolts from here to here, but we don't know the output it needs. we don't know how much gain we need. So the next thing we have to do is design the output stage and then go back and design the gain stage. An output stage is going to be, again, one of those very, very nice emitter-follower circuits. So we're going to do a second emitter-follower.
Excuse me, Professor.
Yes.
Can you go back a slide?
Yes. I will kind of break it into sections. Sorry, I don't like getting this messed up on here. I just run out of space. I don't want to change slides on y'all too fast. Let me know when you're ready.
Yeah, thank you.
Okay. And so our output stage is just going to be another emitter follower that we can design a little bit differently because we actually don't have to do quite as much work. But this time I have to take into account RL equals 8 ohms, which is that speaker itself. So we're going to an 8 ohm speaker. Ground, and this right here, call V, V4. This is a 4-stage amplifier, because we'll talk about why it's got 4 stages. This is RE4, RL. And again, this is that 12-volt signal. So overall, we have a very, very large circuit. This is essentially another emitter-follower amplifier. But this time we take into account the load, because that 8 ohm resistor load is going to play a large role in this, because as we've shown before, this is basically going to dominate here, because if these two are in parallel, 8 ohms is very, very small. No matter what we really set for RE4, it's really going to drag everything down. This coupling capacitor right here, that's what we call it, has a very important role in preventing DC signal from going through your speaker. DC signal going through your speaker sounds terrible and can mess up your speaker, actually. It just really distorts the signal otherwise. So this coupling capacitor prevents that. We want an average power of 0.1 watts to be delivered to the load. So we want this to be power. Which means the RMS value of the load current is equal to PL equals IL squared RMS times RL, which is 8 ohms. So 0.1 watts equals IL squared RMS times 8, which means IL RMS is going to equal 0.112 amps. Which means our peak output current, IL peak, which is what we've been working with so far, so we need to keep, is equal to that times square root of 2, so it's 0.158 amps. Which means we can get our V out peak from Ohm's law. It's going to equal IL peak times 8. So it's going to equal 1.26 volts. That's the V out we want from this part of the circuit. It's a very large value, right? We went from, 10 millivolts to 1.26 volts that we want across here. So that's important to keep in mind. We will assume, again, the output power transistor has a current gain. So this one right here, we're actually going to assume it's 50. Because we want to use a smaller one in this case because we're trying to isolate some things. And we will set a couple of different things. We'll say I EQ 4 equals 0.3 amps. So the quiescent current through this is 0.3 amps. And we'll say that VCEQ 4 is again 6 volts. That's very helpful to us for lots of reasons. It's good, really in the middle of the design for that curve, gives us the most stability, is the biggest reason. We want it to be very far away from that saturation region of the BJT. We want it to make sure it's in the center forward active region. So we designed this way. That means that RE4 should equal 12 minus 6 over 0.3. This actually is IEQ in this case. Volts, that's amps. That's going to equal 20 ohms. So from there, we can find ICQ4, which is this right here. And that's going to equal beta 4, which is that 50, over 1 plus beta 4 times IEQ4. If you don't recognize this equation, you probably haven't watched the videos yet online. When we first derived through how a BJT works, we actually talk about a different parameter other than beta that we call alpha. And alpha is a relationship between the collector current and the emitter current. And it's always slightly less than 1. And alpha is equal to beta over 1 plus beta, essentially. And so this is alpha times IEQ4, which in this case will be 50 over 51 times this. And so that'll equal 0.294 amps. That's ICQ4. And the reason we need ICQ is so we can get R pi. So R pi, for this case, again, 4, is equal to beta 4 times VT over ICQ4, which is going to equal 50 times 0.026 over 0.294. Notice that we didn't allow the rounding to happen in this case because it makes a large difference. And so this will again equal 4.42 ohms. We just derived through how to get the different signals for this. We're actually ignoring a lot here because we're basically going to assume that the output of our gain stage is what's inputted directly into here, and our biasing comes from that stage. We're assuming everything from our gain stage comes right through here. And in that case, we can say that AV4 is equal to V out right here, 4 over V out 3, where V out 3 equals VB4 right there. These two are equal to each other. So basically the output of our gain stage is going to feed directly into this set. We're not going to have any extra biasing to worry about. Which means we can say that 1 plus beta 4 times RE4 in parallel with RL, 20 ohms and 8 ohms, very small values, divided by R pi 4 plus 1 plus beta 4 times RE4 in parallel with RL. So essentially we're ignoring any form of loading resistance coming into here. Which just means this is 51 times these two in parallel, 20 in parallel with 8. So I'll just do it real fast. 20 so this is 51 times 5.71 divided by 4.42 plus 51 times 5.71. Essentially ignoring any load resistors coming into here that would give us loss. In that case, that's going to equal 0.985 volts per volt, which is exciting for us because now we have everything we need to figure out what our final voltage out of here should be. So since we know that we need to know V out 3, AV4 is V out 3 over V out 4. We just multiply, we just divide V out 4 by that gain. So V out 3 is going to equal 1.26 volts divided by 0.985 volts per volt, which will equal 1.28 volts. And I'm going to come back to this slide just so y'all can finish working on it. But I want to point out, if we go back to this stage, that means our input to the gain stage is 8.92 millivolts, and our output to the gain stage is 1.28 volts. So it's a very large gain we have to apply here. And if you were paying attention, I was calling this 4, this one 1. I didn't really call it 1 often enough as I was doing it, but this is gain stage 4. That means we're actually going to have a 2-step gain in this middle right here. We're going to use 2 distinct amplifiers to give us our gain, because we have such a large gain, we don't want to try and do it with a single amplifier. And I'll give you all a minute to catch up with that. Is everyone ready for me to move on? Any objections?
Yes.
Okay, y'all ready? Okay. Okay, so our gain stage is the hard part. And I say it's the hard part. We're thankfully going to make it a little bit easier on ourselves than we could, because we've done a couple of things. For the first part, we ignored the fact that there is some resistance coming through here, and we're going to ignore it again when we go solve the output stage. But we're going to use a 2-stage amplifier. This allows us to get a larger gain than we would normally obtain, and we're going to do it in a way that's designed to be very stable, which is important to us because we want to have high stability in our circuit. We don't want things to kind of have small changes that lead to large variations in our signal. So this is R3. And R4. In here, we have Ri2, which is in V out 1, which is basically resistance coming out of that initial gain stage. And all of that goes to ground right here. And so we go through our first, or technically our second transistor, that we're going to call Q2, which has beta 2 equals 100. I'm actually gonna, both fits. And this is RC2, which actually shouldn't be RC2, but because we don't have an RC1 yet, but it's okay. We're gonna leave it like that so we know it goes with Q2. And this is RE2. Sometimes you skip the number 1 or other numbers just to make sure you're consistent with your transistors. That's what I recommend. That's what the book is doing there. That's what I recommend doing as well. And we take that output right here of this amplifier and feed it directly into our next stage, where this is R5, R6, and that feeds into this. Draw a resistor. RC3, and then RE3. And the output of this is what's feeding directly into IB4, and this is V out, or VC3 equals VB4. Just keep that in mind. So we know what we want this value to be right here. We want this value to be, also this is beta equals 100 as well. We want this value to be 1.28 volts. And we want this value to be 8.92 millivolts. Which means we have to get a gain of this overall circuit, AV, is equal to 144. which I guess I could show you the math, which is equal to 1.28 over 0.00892. We're a gain of 144. It's a very large gain. But we can do this in steps, and we don't have to have anywhere near as large a gain because the gain of this one gets multiplied again by the gain of this one. So if both of these had a gain of 12, it would give us what we need. We're not going to do that just because there's a simpler way of doing this instead. We're going to assume that this one right here has a gain of 5. I want this amplifier to have a gain of 5, and I want this amplifier to have a gain. So AV2 is going to equal 28.8, and also the AV3 is a gain of 5 to give us that 144. You could do 12 and 12 if you wanted to. The reason we don't is we have a larger gain here and then a smaller gain following that. It's a little bit more stable in case you have something that gets out of bounds on the first or the second one. And it gives you a bit more stability. These resistors right here also give us a lot more stability. Remember we went through our design of our BJTs, we could get a pretty large gain with a BJT amplifier like this if we didn't have the emitter resistor. But that emitter resistor provides a lot of stability to fluctuations in our signal, or fluctuations in our DC value, or fluctuations in our beta value for our transistor. These add stability. Without these resistors right here, we have a large amount of instability. And you're actually hopefully going to do a lab where you actually test that. You should actually be able to see that in practice in lab. What's nice about this circuit is we can just break it into 2 stages. We solve this one, and then we solve this one. 2-stage step-by-step work. And again, we have to do a couple extra things here. And again, remember this is 12 volts. We're going to assume that VBE ARN for all transistors is equal to 0.7. We're going to assume that VC3, which is right here, is equal to VB4, which is equal to 6 plus 0.7, which is 6.7 volts DC. The reason for that is when we designed this one right here, we said that VCEQ is 6 volts, which means this value right here is 6 volts. And then we have a loss right here of 0.7 volts, which means when we go through and solve this, since these don't have a capacitor between them, we know that this node right here must equal that 6.7 volts, or else we design our circuit wrong in some way. So we can then just set our base current to kind of pick a base current and work with it. IB4 is equal to, well, we don't actually start saying it. We said it previously in this design stage. Again, IB4 is equal to ICQ over 50, which ICQ4 is 0.954. So that means IB4Q is equal to 0.294 over 50, which is equal to 5.88 milliamps. It's a large value for IB4, which is the other reason we want a small gain for right here, because we already have a very large IB4 current command here. But it's okay. So that means ICQ3, which I know this is getting a little bit complicated because we haven't done some of this connection like this before in DC. We know that this current right here is 5.88 milliamps. We know that ICQ3 has to be greater than that because, again, these have to be different values. But we also know that this current right here, IBQ3, is equal to, actually, I should bring in these, sorry. Okay, let's try this again. Coming out of right here, we have 5.88 milliamps going off this direction. We know that ICQ3, which is the other output of this node right here, equals beta times IBQ3. And we know that this value right here, IRC3, is equal to ICQ3 plus 5.88 milliamps. So we have to design this in a way that's actually helpful to us. And so what we're going to do is we're going to pick this value and make our life a little bit easier. We're going to say that ICQ3 equals 15 milliamps, which means IRC3 equals 20.88 milliamps. And from there, we also know that this node value right here is 6.7 volts. So 12 volts minus 6.7 volts divided by 20.88 milliamps will give us RC3, which is going to equal 254 ohms. We can also go ahead and solve for our pi 3, and that's going to equal beta 3, which is 100, times VT, which is 0.026, over 15 milliamps, and that'll equal 173 ohms. Any questions so far? Okay. Again, we have to go back to look at this circuit again. I probably should just draw it on here at this point. To solve for our resistance going out this direction. So we have a resistor going off this direction right here that we can call RI4, which again we skipped over when we solved this. RI4, which is the resistance this direction going into this, is equal to R pi 4, which we solved earlier, plus 1 plus beta 4 in parallel with RL, which is at 20 ohms and 8 ohm resistor. And so that's going to equal 4.42 ohms plus 51 times 20 in parallel with 8, which is going to equal 296 ohms. That's this resistance right here, going off this way, RI4. This is a very hard problem. Don't panic when you see this. But it's a good practical application of all these different circuit elements we talked about before. So we now know a lot about this circuit, and I'm going to draw it in a way that's a bit cleaner, have a bit more space to work with. So we now know this value right here is equal to 254 ohms. Coming off of here, we have a path to RI4, which is equal to 296 ohms. This is 5.88 milliamps. And from here, we have a path into the transistor, which is 15 milliamps. Out down this way through our E4, R5, R6, then coming into here we have Where is it? No, it's not. Okay. All of this. And again, coming into here, we have 8.92 millivolts. And coming out of here, we have 1.28 volts. Okay. Again, this is a lot of work. And the reason we had to do all this is because we didn't have a capacitor decoupling these. It allowed our output gain stage to be a little bit more simplified, but it also makes this calculation right here a lot more complex. So from there, we can say that a couple things. AV3 is going to equal Vout3 over Vout2. This is equal to Vout3. That's going to equal beta times RC in parallel with RI4. And that's what we had to worry about that. We had a path, again, this way to ground and this way to ground, divided by R pi plus 1 plus beta times RE3, which is our emitter resistor value right here. I'm sorry. This should be RE3. I apologize. This emitter resistor value right here. We don't know what this is yet. We haven't solved for it yet. But we can solve for it by saying, okay, well, we want AV to equal 5. We know everything else. So we can say 5 equals 100 times 296 in parallel with 254 divided by 173 plus 101 times RE3. Then we can rearrange that and solve for RE3. And we should find that RE3 equals 25.4 ohms. Very small value, which makes sense. From here, we can do a little bit more work. We can say that R5 in parallel with R6, regardless of the values, is going to equal 50 kilo ohms. And then we can solve for, okay, well, we know this value right here is 6.7 volts. We know the value for IBQ. We can solve for R5 and R6 from the fact that these should be the same. We can get R5, I'm not doing this step just because we don't have time, is equal to 69.9 kilo ohms, and R6 equals 176 kilo ohms. The book doesn't show you how it does it, unless this is a DC step. The way you would do this, again, you know the value for IBQ is equal to ICQ over 100, so that's going to equal 15 milliamps over 100. You now know everything you need to solve for R5 and R6. If you pick a value for them in parallel, you can rearrange this and solve for these two values in terms of VBB. It's a lot of work, but it's not impossible to do. So now we have this equals 25.4 ohms. This is 176 kilo ohms. This is 69.9 kilo ohms. A lot of work, but we're getting there. A whole lot of work, but we are getting there. And so now we can go through and solve this half of the equation. I know, it's a lot. So we're going to pick a couple values right here, RC2, RE2, R3, and R4. And again, we're working back this direction. We can say that RC2 equals VCC minus what's called VC2 divided by ICQ2. We can just say that this is equal to 6 volts. This is equal to 5 milliamps. Just pick values for them that would be nice in the center of the forward active region. And we'll get the ICQ is equal to, RC2 is 1.2 kiloohms. This one's a little bit easier because you don't have to worry about interaction with this half of the circuit. This capacitor right here decouples these two gain resistors, which is very nice. 1.2 kiloohms. From there, we can say that R pi 2 is equal to beta 2 VT over ICQ2. We said this was 5 milliamps. This is a constant. This is 100. So this is going to equal 0.52 kiloohms. And that means Ri3, the resistance going into here, which is why we had to solve this half first. This is the only way they interact, is equal to R5 in parallel with R6 in parallel with R pi 3 plus 1 plus beta 3 RE3. Which is going to equal 50, which is what we said a minute ago, in parallel with 0.173 plus 101 times 0.0254. And that's going to equal 2.6 kiloohms. Again, we had to know the fact that once we short this out, we do have some resistance to ground here. And we can go through this direction, through here, or down through here to ground. So there's a lot of different ways they can interact. Yeah, I know. This is a long circuit, and that's okay. This is harder than I would give you on a test, but it's a really good practice problem. And I do one like this in videos too, just without this extra stage over here. So from there, we just need to know a couple extra things, and I'll come back to this if you want to see it. Because remember, we have, again, we'll call this R. So from here, we can do a couple extra things. We can say that AV2 over 2 C2 in parallel with Ri3 2 plus 1 plus beta 2 times RE2. Again, we have RT2. We just solved for Ri3. We solved for R pi 2. We have all these values again, so we can say 100 times 1.2 in parallel with 2.6 kiloohms divided by RE2. So our answer is going to be in kiloohms. If you're paying attention, no, I'm not if you're paying attention. Our answer will be in kiloohms, but we're going to write an answer in ohms. So 28.8 equals all of that. And we'll find that RE2 is equal to 23.1 ohms. Again, a very small value. And that's because, again, we want to, it's to stabilize our circuit, but it's not to mess up our gain too much. Which finally, if we set that R3 in parallel with R4 is equal to 50 kiloohms again, we find that R3 should equal 181 kiloohms and R4 should equal 69.1 kiloohms. And we have all of our values for our circuit now. This is 23.1 ohms. This is 69.1 kiloohms. And this is 181 kiloohms. As with any design problem, there is no unique solution here. I could have made any number of different design choices as I was picking these values. Like for example, when I set this is equal to 6 volts. Sorry. When I set this equal to 6 volts, I could have picked 5 volts instead, and it would completely change my entire answer. But it's going to give us similar results as long as you do it correctly. Also, if we wanted to actually build this with real units, we'd have to pick values for resistors that made more sense. We actually might pick our resistor values first and work backwards from there. Because a 1.2 kilo ohm resistor isn't that easy to come by. A 23.1 ohm resistor is definitely not easy to come by. So we want to make sure we take that into account as well. Some of these things would be rounding errors, and we could round it off that way and call it good. Some of these would play a large role, so we have to make sure we pick our elements correctly. Finally, we completely ignored the role of this 50 kilo ohm resistor in parallel with this pathway right here. Like we said, we had to deal with that every other time when we solved it. We ignored that in our initial stage. Hopefully, it wouldn't play a large role, but we could go back and see how off we are from that, and we have to iterate. We don't really want to have to do that, so we're not doing that today. Are there any questions on how we approach these kind of problems? Again, what I really want you to see is the design aspect of it more than anything. So we had to deal with that 10 kilo ohm resistor, so we isolated it using that common collector or emitter follower design. We had to match our power limit specifications, so we figured out the current and then figured out the voltage from there. We had to get a very large gain, and we wanted it to be stable, so we had to use a two-stage amplifier. We have to worry about how all these parts interact as we're going through things. These are all important things to think about when you're doing design. And as EEs and BMEs, there's BMEs in here, design for circuits is a very, very important part of your job. Computer programs will help you out with it, but knowing how to think through the process is more important than anything. The computer program would have done the annoying part where I was going through and solving the math, right? But thinking through the process, you have to know how to do. And thinking through what's required of your circuit, you have to know how to do. You also need to know how to do the math too by hand. But the design process is really important, so I want to make sure we think about that a little bit. Are there any questions on this circuit? I ran over time. I'm so sorry, guys. We are running late. I will see you all next time. Hey, if you could write down who was there real fast, that'd be great.
Can you go one slide forward?
Yeah. I'm sorry I ran long. I lost track of time. Yeah, and I'll leave this up for a minute.